Welcome everyone. This is on. Welcome everyone to today's physics colloquium. I'm here to introduce Adam Kaufman, who's our speaker for today. I'm sure he's going to give a fantastic talk. If you've ever heard him talk before, he gives great talks. So I hope you enjoy it. I'm going to tell you a little bit. Actually, Adam's been here a while. He actually came to us in 2009 from Amherst and did his PhD with Cindy Regal. He did it on trapping rubidium atoms and tweezers and seeing something called a Hongo-Mandel interference between these identical particles, sort of something you normally see with photon fields, actually seen with atoms. He was awarded the Demopp Thesis Prize associated with that PhD work. He then went away for a brief vacation in Harvard in Marcus Greiner's group, where he worked on measurements of entanglement entropy associated with thermalization in closed quantum systems. He then came back here and joined us at JILA in 2017. And since then, he's been a very, very active member of the community. We've had the pleasure of interacting with him. He's sort of a force of nature when it comes to sort of organizing grad recruiting and helping. If you remember during the peak of COVID, do you remember Gather Town? Sort of going around, okay, that was Adam, all about that. So we could actually interact with visitors and sort of talk about what we have here. Boy, at the time, that was so much better than having to set up Zoom meetings individual, and it's the best we could do. But more broadly, he's had an impact. You know, locally, he's organized the qubit seminar, which brings in sort of world-famous speakers to interact with us and tell us about the research. In addition, he's the organizer of something called the virtual AMO seminar. Again, at the height of the COVID, there was a need to sort of still share what was happening in our labs and in our theory groups. And this has become a wildly popular online event within the atomic physics community and continues. He was awarded the 2020 Young Investigators Award from ONR. And in 2023, people really began to cotton on to sort of what's been happening in his lab. He's been doing fantastic stuff here. And so he was awarded the Robbie Prize from APS. In addition, he was awarded the New Horizons Prize in Physics and shared that with several others. So with that, let's welcome Adam and hear about his latest and greatest.
Thanks a lot, James. Happy face. Okay, this is good. This is good. Okay, so Leo, thank you so much for the invitation to speak here. So in putting together this talk, I basically explicitly neglected the advice that we gave speakers who were coming through in the Colloquium series, where we said, like, come up with like a very coherent, narrow story and tell that in detail. Instead, because this is internal, I wanted to make sure that I covered the various things that we're thinking about in my group in hopes that maybe this might spark new collaborations and things like this. So if the talk is a little bit dense, I hope you'll forgive me, but if I don't get through all of it, that's totally fine with me.
You mean you disobeyed my instructions?
Almost certainly. I mean, well, but I obeyed other people's instructions about your instructions. Yeah. Okay. Good. All right. So the work that my group does and many, many groups in Boulder do falls into this broader category of quantum information science, represented by tasks like quantum communication, the ability to transmit information in ways that is more secure than is possible with classical resources alone, tasks like quantum simulation, quantum computing, and also even metrology. And as I said in the case for quantum communication, the sort of underlying theme for all of these directions is leveraging aspects of quantum mechanics to do things that are less possible than with just sort of classical resources alone. And to start, I just wanted to point out that these capabilities really arise from the basics of quantum science, or sorry, quantum mechanics in general. And so this is really basic just to begin, right? So let's imagine that we have just one spin. This could be the spin of an electron. If we measure that spin, we'll always find that it's up or down. But of course, before we make that measurement, what quantum mechanics says is that it can also be in a superposition of these two conditions. So this is an important feature of quantum mechanics, which is important to these applications that I was just describing. And this sort of these properties persist as you add more and more particles in more important ways. So for instance, if we have two spins, say a spin at location A and a spin at location B, these two spins can be in four possible states. up, up, down, or down, down. But one possibility, if I pick two of these, is that you have a superposition of up, up, and down, down. And we say that that's an entangled state because even though the outcomes of my measurements in this system would always be fluctuating, some of the time I find that the spins were up, other times the spins were down, they were always correlated in their outcome. And this is a very bizarre feature of quantum mechanics. And what's odd and also very important to these applications is the fact that these properties persist even over macroscopic length scales. So for instance, I could separate these spins over a kilometer, and I'd find these exact same properties are maintained. So that's 2 spins. You can also have n spins. In that case, there are 2 to the n possible ways of writing down the outcomes of our measurements. And in general, the quantum state that describes this full system is described by 2 to the n amplitudes, which is basically to say that this state stores a ton of information. Sort of the way that we often talk about this is by saying that Hilbert space, the space of quantum states, is quite large. And so it is really the combination of these 3 features that underlies many of these applications that I was just describing on the previous slide. So just to sort of give in detail 2 examples of how these things can be used, we can talk about quantum computing. And so we can ask the question that people ask a lot these days is sort of how long does it take to factor a 2048-bit RSA key? An RSA key is the thing that we use to encrypt information on the internet. And importantly, the fact that this problem is quite hard for a classical computer underlies the security of many systems. So we can sort of imagine asking, how does the classical computer compare to the quantum computer? I've drawn a cartoon of a classical computer here. Anything I'd put in this box would be controversial. So instead, I'm going to put a picture of Peter Shor, who came up with this algorithm that's relevant here for quantum computing. And the point is that using Shor's algorithm, on a quantum computer, this would take polynomial time to factor this number, whereas for a classical system, it would take exponential time. And so in real numbers, what this means, depending on whom you speak to, is that on a quantum computer, this could take 8 hours to days. On a classical computer, this would just be unrealistic. So it takes less time to factor. The quantum system enables a speed up. OK, so that's one context. Another context is in metrology. So one thing that people often do is they probe the energy splitting between 2 states in a quantum system. And that energy splitting might be proportional to some parameter of interest, say the magnetic field in your lab. And you can ask the question, how well can I measure this parameter B, the magnetic field, for an unentangled system? And what you'd find is that you can do this with a precision which is proportional to 1 over the square root of the number of particles that you have. This is just from projection noise, the fact that I'm flipping like n coins, there's a distribution in those outcomes. By contrast, if I have an entangled state, say a state of a superposition of all of the spins up versus all of the spins down, then there's actually an enhancement in your precision. And the upshot of this is that it means I can make fewer measurements on copies of this system and get to the same precision as I would for the entangled system compared to the unentangled system much more quickly. So in that case, too, you have a speed up to get to the same precision. OK, so given these 2 examples as motivation, how do we get to these kinds of capabilities? And often this begins with having well-controlled single quantum objects, I'm calling them. And there are many examples of these quantum objects these days. They're trapped ions down the road, photons in cavities, like in James's lab and June's lab, superconducting qubits here in Conrad Leonard's lab and also at NIST, neutral atoms and tweezers, like in my lab and in Cindy's lab, NV centers in Shuo Sun's lab. There are many examples of this. And so what I want to point out to begin with is that even in this limit where you have just a small number of quantum objects, there are applications of interest. So for instance, optical atomic clocks down the road, which have sort of proceeded over a long length of time to really push the envelope of what's possible with time and frequency precision, just with a couple ions. There are also Bell tests that were done that showed violations of sort of basically showing that quantum mechanics is almost certainly correct. So even in this small limit, there's a lot to do. And I'd be remiss if I didn't point out that just doing this led to Nobel Prizes. So for instance, everyone's familiar with this guy here. I realized that Serge Haroche's picture came out sort of blurry on the website for the Nobel laureates, so I I don't take responsibility for that, but nevertheless it did. There also was the 2022 Nobel Prizes, also in this same category, where instead of using individual quantum systems like photons or ions, they were using entangled photons in order to measure violations of Bell inequalities. Okay, so given what will be the focus of this talk, it's important that I point out as well that in 2018, optical tweezers were also awarded the Nobel Prize, but in this case for applications to biological systems. And what I'll be telling you about today is not about biological systems, this is a physics colloquium, but rather using optical tweezers to trap atoms and do quantum science with them. Okay, which is a nice segue. This previous work that I was just describing sort of is in this few particle limit, but there are many applications, some of which I already discussed, which belong in the category of having many qubits or many particles. And so the question is, how do we get to that regime? And it's important because really, for many applications, the ability to generate, maintain, and control large-scale entangled states, that really is just sort of the thing that we need to do. And one way to get there is to start by building complexity from well-controlled individual qubits or particles. So examples of this these days are superconducting qubits. This is a picture from the Google experiment. Trapped ion systems. This is from Rainer Blatt's group, where they have, I think, actually up to 50 ions now. And then in neutral atom systems, there are actually two examples of this these days. There are the quantum gas microscope systems, where you have atoms trapped in a standing wave of light, known as an optical lattice. And you can image and control those atoms using a microscope that's placed above that system. And there are also optical tweezer arrays. And so in this talk, I'm really going to focus on these two guys here. And given my history and also where a lot of our techniques begin, I'll start with the story about optical tweezers. OK, so by optical tweezers, just to make sure that we're all on the same page, and this actually is one of the more technical slides. Like, I'm not actually going to go into that much experimental detail about how these experiments look, so just feel free to ask me questions. These experiments look as follows. You have a microscope. These are important. They have to work right. You put light into this microscope. And typically, the atoms not typically, always the atoms that we trap are in an ultra-high vacuum environment. So we're focusing this light through a microscope that goes through some vacuum window in our case. That's what this blue thing is here. And then we trap the atoms inside using the field made by the tweezers. So basically, the tweezers make an attractive force that allow us to hold on to single neutral atoms. And importantly, the same microscope that's used to make the tweezers, the green here, can also collect fluorescence from the atoms and make images like these. So this is an average image here showing you single atoms in a 4x4 array, in this case strontium atoms. And this is based off pioneering work from the Grandier group in the 2000s. Over the past, basically 12 years or so, there have been sort of a growing number of applications of these systems. So for instance, they've been used for few to many body physics, using the fact that you can shape the light field that you put into the tweezer and then make multiple different spots whose positions and depths and all sorts of things about them you can control in real time. So this has been used, as I said, for few to many body physics. Also, the control afforded by these systems has allowed people to do things like quantum information processing with neutral atoms, where you can really, at a single qubit level, where the qubit here is some internal degree of freedom of the atoms, control and sort of produce circuits in a quantum information context. At JILA, in a collaboration with the Yi group, we've been exploring actually how these systems can be used for optical atomic clocks and metrology. And finally, I like to highlight this work from the CUA, an experiment at Harvard, because I think this is a very creative application of these, where you use atoms trapped in tweezers, and the fact that the atoms are so well localized in these systems allows the group to bring atoms close to nanophotonic devices like these here, and then map internal degrees of freedom of the atom onto photonic degrees of freedom that travel in space. So this means you could imagine linking up sort of different quantum processors using this kind of technology. OK, so one thrust over the past several years has been to expand this optical tweezer toolset to more complex atoms. So This is a theme which actually is parallel with a lot of what happened with Bose-Einstein condensation. People began with alkali atoms, which have a single electron in their valence shell. These are just easier to manipulate and control. And so by more complex particles, what I mean here is basically not alkali atoms. And so this is represented by work such as at the CUA, where they trap molecules in tweezers. And I should actually add more groups here. There's now a group at Princeton that's also doing this, at Lawrence Schuck's group. They're dual species experiments, which is 2 alkalis, which is more than 1, which is why I'm not being inconsistent. And this is really beautiful work from Hannes Bernian's group at Chicago. And then finally, in my group at JILA, Emmanuel Andres' group at Caltech, and then also Jeff Thompson's group at Princeton, the 3 of us at around the same time all began looking at trapping alkaline earth atoms in tweezers. And as I go along in this talk, what I'm going to try to do is as I go, explain how features of these atoms enable the physics that we're looking at. Yeah.
If we're going, can you contrast the sort of capabilities that tweezers give you over like optical potential?
Oh, I'm going to get there, actually. Yeah. OK, so using these kinds of systems, my group is looking at 3 different things. So we've been looking at quantum metrology, the idea of using entanglement to improve our ability to do measurements. We've been looking at ideas related to something called sampling problems. So if you were at Scott Aronson's talk, you might have heard about this. But the basic idea is that there's a certain class of problems that you can look at that are provably difficult and yet are accessible in experimental systems in a way that is near term. And then finally, also looking at quantum information using a particular species of atom that we really like, known as ytterbium-171. OK, so in this talk, my goal here is to first describe this direction that I was talking about in the middle there, sampling problems with programmable bosonic atom arrays. And then I'm going to have a shorter section at the end of the talk, which talks about 2 directions which leverage the different 2-level systems that are accessible in alkaline earth atoms. All right. And this is going to get to your question here, Leo. So this section of the talk is really focused on the idea of how to gain scalable control, how to gain control of large quantum systems at a single particle level. So having microscopic control of large arrays of qubits or atoms. And in the context of neutral atoms, there really have been 2 platforms that have been doing this, as I mentioned earlier. There are the quantum gas microscopes. And here you have this microscope, and it allows you to look at the physics of so-called Hubbard models. And what I mean by that are models in which the atoms are free to move around in a standing wave of light, the lattice. And it's more that they're able to move around. It's the fact that they're actually able to coherently tunnel. And furthermore, they can interact in this lattice. And so these systems allow you to have single, basically snapshots of many particle wave functions that are atom resolved of the physics that actually is believed to occur in real solids. So this is a very nice system for studying the physics of potentially what goes on with electrons in, say, a crystal. By contrast, there are also tweezer arrays. And here, a lot of the work that's been going on, and I'll later talk about other examples of this that go against this, what I'm saying right now, but a lot of the work that's been going on has been in studying spin models. So rather than looking at itinerant physics, one is looking at how, say, quantum magnetism arises in some interacting model of spins. And one of the reasons this is possible in particular here, and this is getting to Leo's point, is that you can really choose where the atoms end up nearly arbitrarily using these systems, whereas in these itinerant lattice systems, it's pretty hard to do that. So basically, there's a lot more control here, and each of these things look at different physics. And so the question is, can you combine the sort of programmable control that you have in the tweezer system with the itinerant physics that you observe in the quantum gas microscope systems? OK, so there have been a lot of efforts motivated by that question. So one, this is a picture from my postdoc work. So this is known as cookie cutting. So the idea is you load some gas of atoms, you make it really cold, you'll have something like 10 to the 6 atoms, you load it into a lattice, and you drive this many-body phase transition. I don't want to talk about the details of this. And then you end up with, say, 1,000 atoms where you have like pretty good occupation of the lattice sites. They're just either, like most of the time, you have 1 atom per lattice site. Sometimes you have a hole. And then with those 1,000 atoms, you then cut out some much, much smaller sample and use that as a way of getting to the sort of programmable control of the initial conditions of your system. So this has some nice features, but it's also challenging because you still suffer from residual defects in your system. And also the data rate is extremely painful. So for instance, in my postdoc work, every single time we took a run of our experiment, it took a minute. For analogous things that I'll show you later in this talk, it takes 1 second. So another direction that's being pursued was both pursued in Cindy's group, actually when I was a PhD student, and also more recently in Wasim Bakker's group with fermions, is the idea of actually using the tweezers themselves to prepare Hubbard models where the atoms can tunnel between the tweezers. This is a really nice direction in the sense that you have all the control that I was discussing earlier, but it has some challenges too with making all of these different potentials exactly at the same energy, which is needed for looking at itinerant physics. So in my lab, one of the things that we've been looking at is a different approach to this, which is basically the brute force approach of smushing the two technologies together. So what I'm showing you here is a picture of a tweezer. We can actually make many of these tweezers, but I'm just showing you one for the moment. And then in red here are the equipotential surfaces of a lattice potential. And the point is basically the atoms are confined in all 3 dimensions via a standing wave of light, but they're isolated to a 2D layer. So we have a layer of 2D atoms, and it's registered with an optical tweezer. So until the time we were doing this, no one had done this before, partly because it's actually very challenging to register these tweezers with the spatial scales that are relevant for the lattice, which is like half a wavelength of a visible wavelength or even near IR.
How large is your beamwidth compared to the atomic spaces?
Yeah, so So for this particular picture here, the waist of our tweezer is 450 nanometers. And the spacing here between lattice sites is 575 nanometers. OK, so this is sort of the tool that I'll be describing. But for the physics, I just want to highlight that we're working with strontium-88, which is an atom that, for all intents and purposes, I just want you to think of it as a photon. It's basically non-interacting. Okay? So compared to, let's say, alkali atoms, which would have a much larger scattering length for the experts in the room, this one is sort of puny. It's -2 Bohr. So we just sort of don't care. The next thing that I want to plant in your head is that if I think of atoms tunneling on a lattice, if I think of an atom at a site, sort of at any given time, it has some chance to tunnel to the next site or stay where it started. So you can sort of think of that as the effect of a photon hitting a beam splitter. There's some chance it goes through the beam splitter, and there's some chance it gets reflected by the beam splitter. So you can think of the dynamics of atoms on a lattice as like a bunch of photons traversing a beam splitter network, particularly in the case where these atoms are non-interacting like photons. Okay? All right. So one other ingredient that I want to highlight that we use here is we use, and this is a feature of an alkaline earth atom. So there are all these levels in alkaline earth atoms. And one transition in particular that we care about is this transition between a singlet S0 state and a triplet P1 state in strontium, which has the nice property that the line width of this transition is much less than the trap frequency. And the upshot of this is that you can do something known as resolved sideband cooling, which the trapped ion folks have been doing forever. And the basic idea is that you can drive a transition which reduces the vibrational quantum number while flipping the spin of the electron. And then the atom decays. But if the trap is sufficiently confining, it stays in its reduced vibrational quantum number. And you can iterate on this process over and over again and accrue a large ground state fraction. And in particular, the occupation, the mean occupation in the ground state, looks like gamma over 2 omega squared. So as this number approaches 0, you get more and more ground state population. And what one finds, if you just do the basic calculation, is that for our system and with these parameters, we expect to be able to very quickly laser cool this system to its ground state to 98.5% 3-dimensional ground state fraction, just using laser cooling. One other point that I'll make is that the combination of this efficient cooling with detection off a different transition allows us to do high-fidelity images of single atoms in these experiments, too. OK. So here's what our experimental sequence the sequences look like. So we load a tweezer array. This is sort of an ugly image because the tweezers that we use here are just not so great for imaging. And so we load this array, and that allows us to isolate a plane of atoms. And these are images of atoms. We then can implant the atoms into a lattice potential. And so this picture here is an average image where we move the tweezer array across this standing wave and then take an image. And we take many of those images so that we can see the underlying corrugations of the lattice. So I'm basically just trying to show you here that we have a large number of lattice sites into which we can implant the atoms. We then use the tweezers to rearrange the positions of the atoms. A sort of annoying feature of these tweezer systems is the fact that you stochastically load. You either 50% of the time get an atom, or you 50% of the time don't get an atom, but you don't get two atoms. So it's either 0 or 1. But we can image them non-destructively and then rearrange them based on that information. And this is based off pioneering work from the Lucan group and Antoine Brouwese's group. And make pictures like these. So this is an array of atoms on nearest neighbor sites. So these are each 2 atoms next to each other. This is an array of atoms in every other site. This was the cute thing the folks in the lab decided to do of strontium-88 pointing at a strontium-88 atom. And then this is just us trying to rearrange a lot of atoms. So then once we've done that, we cool the atoms to their ground state, and then we let them go. So for the experts in the room, we do psi-band spectroscopy to check the temperature of the atoms. And we see that they're basically within our precision and have greater than 95% 3D ground state fraction. And then we let them go and allow them to tunnel, and then we detect where the atoms end up. Yes?
So I'm trying to understand, so like, do you have a tweezer on every minimum of the optical potential? You have
Yeah, so when we implant, we align the array such that it puts the atoms at, yeah.
Right, and the confinement from the tweezers is stronger than the optical potential, so when you move the tweezer,
Yeah, so this is like a sort of a dance here where we make the lattice sort of shallow but not too shallow so we can't cool, and we're moving them around and making sure we drop them off where we want to drop them off, and you're sort of balancing a bunch of stuff as you do it. Yeah, and then we like check where well, it doesn't matter. Yes, that's what we do. OK, so let's check sort of at a single particle level whether this basic scheme works. So the idea here is we implant an atom at this location here where there's that circle. We can then run our experiment many, many times and accrue an average density pattern associated with the wave function of this atom. So each blue smudge in this video here is the location that we found the atom. And we find that we see an interference pattern, which is exactly what you'd expect theoretically from the 2D quantum walk of this particle in the lattice. So that's like a check. This is working. You can go to larger tunneling times and see that this wave function spreads out. And even at fairly late times in the tunneling time, you can still see fringes in the distribution. This is nice because basically the physics of a quantum gas microscope, we're able to access a much faster timescales. We could take up to 50,000 shots per day. We can even do experiments in parallel as long as the atoms don't overlap. And then one thing I want to highlight, not only can we control where the atom begins and its dynamics, we can also in real time control the unitary that the atom experiences in the system by, say, shining a very weak tweezer on one site and changing its depth. And this is actually relevant to some work that we did in 2022, where we were able to realize this proposal by Andrew Childs for a spatial search algorithm occurring within a quantum walk. OK, so that was one particle. And now I think all the people who are in my quantum optics course with James are like, oh, wow, he really likes the Hung-Mendel effect. So their homework right now is on the Hung-Mendel effect. So that was one particle. What about two particles? One thing that people often do in photonics is they use this thing called the Hung-Mendel effect to diagnose the purity of the single photons that you've prepared. So let me just briefly explain what the Hung-Mendel effect is. So it's the idea that if I put a photon in one port of a beam splitter and a photon into another port of the beam splitter, for a particular position of the beam splitter, the photons always come out the same port, which is super weird. These are like non-interacting photons. They're not talking to each other. And this happens because of a path interference effect, a two-particle path interference effect, which suppresses the likelihood that the photons come out different ports. This can be understood fairly easily. Now I'm actually giving the answer of my homework. Each of the photons can either come out the same port. Another way of saying this, one can be transmitted, this one, or the other one, or one can be reflected. The same thing happens here, but they come out a different port than this case. Or they can both be transmitted or both be reflected. And these two cases have opposite sign and cancel. And so this realizes the so-called Hangu-Mendel dip, where at this particular position of the beam splitter where the photons are perfectly overlapped on it, you see this dip associated with the coincidence counts, which quantifies how likely it is that the photons come out different ports. Okay? And this only happens if these photons are indistinguishable. So if they are in different polarization degrees of freedom, now I'm giving away the extra credit, this goes away. Okay, so how can we do this in our system? This is challenging because we can't actually measure multiple atoms on the same site. This is a technical issue arising in these systems. But the indistinguishability that we want to see, the fact that these photons or the atoms are exactly the same, is manifest in wave function overlaps. These two things are somewhat inconsistent. And so Aaron, who is leading this project, had a very clever idea, which was the following. We can allow the atoms to expand in 2D such that the number of modes that they're spread out on is more than n squared. Why this is relevant is that if you want to ensure that the probability of a collision, that two atoms end up on the same site, is low, you need to satisfy this condition. This is known as the bosonic birthday paradox. But then we can analyze the experiments in 1D because this is a separable system. So basically, we can look at the physics in a projected 1D space where the density is higher, even though the dynamics are occurring in 2D. So how does this look? So we can have two atoms that start on neighboring sites here. If we wait some amount of time, that's about a tunneling time, we see that their density is sort of smudged out. The density doesn't really tell us anything. What we care about are correlations. And so what we do is we can look at the data this way. Let's look at the number of particles in each column here. So this initial state here is this 0, 1, 1, 0, and then all zeros this way, all zeros this way. Does that make sense for the input state? Just the number. Okay. And then after some time, we get some distribution in the outcomes. And so we can then create a correlation map, which quantifies what is the likelihood that I find a particle at x1 and a particle at x2. So if we look at the top here, the input state, this has is black and is basically 1 because the particles start off on site 4 and site 5. So that's why we end up right there. But then if we wait some amount of time, what we find is that the probability for the atoms to end up in this initial condition where they were next to each other has actually dropped to very close to 0. So this sounds a lot like a Hangu-Mendel effect because I had these two particles on separate sites, sort of like two modes of a beam splitter. And now if I ask whether they end up in those modes, those sites, I find that it goes away. And so to check that intuition, we can also prepare two atoms and different rows in this system. And so now this row is like a distinguishing degree of freedom. It's almost like a spin label. And what we find is that now this probability is actually restored at that location on the lattice. This is sort of removing this effect that I said was probably there, although I haven't proven it to you yet. And so to understand what's going on here, we're starting with some input configuration like this. We have two atoms in neighboring sites. And then the output is some distribution of the particles. And I'm showing you all the paths of the single atoms on the lattice. And so the possible outcomes are this configuration here. This is the one of interest, but there are also all these other ones. But I'm just asking the question, what is the likelihood that this one comes out? What's the probability that I get that at the end? So I can ignore all of the paths here which don't contribute to this. And Leo, you're going to have to help me out in this point here. So I can calculate the two particle amplitudes. And so I have a 1 times a 1 plus an I times an I, which equals 0 in the end. So this goes away, right? And so by contrast, if I had distinguishable particles, then this argument fails, right? Because these two different configurations are actually distinguishable. I get so then I see these in the outcome. Yeah.
When you say and then you talk about time, you're shutting off the tweezer that initialized the particles?
Yeah. So we rearrange, we put the atoms where we want them. We turn off the tweezers so they're gone, but the lattice is still deep, so the tunneling is low, and then you drop the lattice and allow them to tunnel. Yeah.
Adam, in terms of the original sort of photon Mendel effect, how tightly or how well do I need to have sort of the averaged Gaussian beam shapes entering that beam splitter overlapping? Is this like needs to be like 1,000 1,000th of a beam diameter? Or
So this depends on a couple different things, but I mean, basically what you look at is an overlap in a quantized field of these two wave the two wave packets.
so but it's experimentally not impossible to realize this.
No. People use this all the time. Yeah. Yeah, like 100% used all the time, yeah. Yeah, hey.
So why does putting two atoms into the diagonal configuration making them distinguishable?
So imagine let's consider a different situation where they started off on the same row, but they had a spin degree of freedom. Okay, so let's ignore the other direction. So in the Hongel-Mandel case where you see this interference, that spin degree of freedom, we could be driving rotation. So like they could be Rabi oscillating. But if they're Rabi oscillating in exactly the same way, then the interference is going to be there because they're in exactly the same quantum state. But now let's imagine that we do the exact same experiment, except we start this one spin down, right? Then you don't see the path interference anymore because these are always distinguishable as a function of the Rabi oscillation time and the tunneling time. Does that make sense? Okay, so I want to point out that these experiments have been looked at from many different perspectives. So for instance, in Cindy's group, this was looked at in just a double well potential. In Marcus Greiner's group, this was looked at for looking at subsystem purities and entanglement entropy. And actually, even in free space, with like flying atoms, this was looked at in Alan Nespé's group and Christoph Westbrook. This is sort of, so what we're doing here is really just like checking that the physics makes sense basically of what we're looking at. And so what we want to do is look at the ratio of the distinguishable data compared to the indistinguishable data. Basically, this is like allows us to normalize on weird stuff that might be going on in the experiment, which there isn't, but it's just a natural way of normalizing compared to the indistinguishable case that we're actually preparing. And working with Sean Geller and also Scott Glancy and Manny Knill, we've looked at this problem fairly carefully just to basically show that we can see that there's a Hongel-Mandel dip that implies that we have a greater than 95% single particle purity in our preparation of single atoms just using the physics here. Okay, wow, I'm going a lot slower than I expected, so I won't even get to the second half of my talk, but that's fine. Maybe, never mind. All right, so that was two particles, but let's go to more particles. So this is non-interacting bosons, which sort of, if you talk to a many-body theorist, they're gonna be like, oh, that's like super easy. Why are you even bothering with that? But I'm gonna try to convince you with this slide that like this is still a very interesting situation. So let's ask the question, I have some initial configuration like this of my particles, and I have some final condition that looks like this here. What is the probability that I get this final condition given that I had this initial one? And so that will depend on a single particle unitary, which tells you the likelihood, the quantum amplitude that a particle that starts at site J ends up in site K. But I don't only need that. I also need to consider all the ways that these bosons might move on the lattice. So there's the possibility that this guy goes down, this one goes over here, this guy goes over here, this guy goes over here. That's one outcome. And then I have to multiply all the quantum amplitudes associated with that. But of course, there's also this guy, and they're actually like basically n factorial of these that I have to consider. So this problem blows up and gets complicated very quickly. And this is the problem of boson sampling that I think Scott talked about this and other things. That basically the probability to scatter from this, or to go from this initial condition to this final one under this unitary U is basically depends on calculating the permanent of a fairly complicated matrix. And calculating permanence is hard. That was the basic idea of this proof from this paper here. So this has motivated some pretty crazy experiments in the world of photonics. So for instance, this is a picture of just like a crazy beam splitter network from Jiawei Pan's group where they were looking at this. I had a colleague who pointed out that this would be the motivation for all integrated photonics experiments in the future, like just this photo. And this has been done with Fock states of 14 photons and 60 modes, or squeeze states of 70 with 70 states or 100 modes. So let's sort of build up more and more particles sort of in this, or add more and more particles in this context. So we can look at bunching, which is the likelihood that all of the particles end up on the same site in this 1D space. And so in black is what we observe for indistinguishable particles, and the gray is what we observe for distinguishable particles, which we can measure in various different ways in the experiment. And we see that there's agreement between theory in both cases. And furthermore, there's actually an n factorial enhancement in the case of indistinguishable particles. And it turns out that this is true for actually any unitary. So any unitary that I apply on this lattice, I will get this condition. There's another metric that people look at in photonics known as clouding. This is the likelihood that all of the particles end up on the same side of your array, or in their case, the same side of their interferometer. And here, too, we see nice agreement. This particular case is actually sensitive to the exact unitary, so it's testing something slightly different. But nevertheless, the point is that you can see that these outcomes are falling exponentially. So this p bunch and this p cloud, it's getting smaller and smaller, which means our ability to diagnose whether we've prepared an array of indistinguishable particles, that's getting harder and harder for us to do as we add more and more particles. And so the question is, are there sort of more efficient metrics that one can look at to try to get at the idea of whether you're actually preparing a many-body system of identical particles? OK, so to do this, we were inspired by these works by someone named Skesnovich. I'm actually blanking on his first name all of a sudden. What's his first name? Valerie, thank you. Yeah, thanks. And so the idea here is a little bit weird. It's the probability that all of the particles end up in a random set of k modes. So I just choose some random set of modes on the lattice, and I ask the question, what is the likelihood that all of my particles end up on them? And it turns out that for bosons, this is maximized, and for other statistics, it is not. So if I have distinguishable particles, you see a smaller probability, and for fermions, it's actually minimized. So bunching and clouding are just two specific choices of a subset of modes. So the k here is the subset of modes, and k could, in the bunching case, is just all of them ending up on the same set of sites. Okay? So we look at this as follows. We actually go to 2D now. We prepare an array that looks like this, and we let the atoms go. The blue is the density distribution after the atom's tunnel. The red here corresponds to a particular selection of k. Right? This is just a particular selection of modes. There's some important details in how we analyze this data, but what we do is we average over all possible subsets of k, or all possible k. And what we find is that for indistinguishable particles, we can simulate this up to 25 or about 25 particles. Yeah, it's 25, right? Yeah, 25 particles using this algorithm from 2018 called Clifford and Clifford. And the idea is we see good agreement up to that point. We can't simulate at 36, but that's not a statement of like quantum advantage or anything like that. It's just that like what we have at our disposal does not allow us to do that. For distinguishable particles, we see also good agreement. And importantly, we can simulate what the effect is of adding distinguishability to the system just via the temperature. So if we allow the atoms to be a little bit hotter, we can see that numerically in calculations, we go from what we observe in the data to more and more closer to what we have with distinguishable particles. So this is showing that A, the experiment is working pretty well, and B, that this sort of odd probe is actually making sense. It shows us that as we get hotter and hotter, this system looks less and less like an indistinguishable array of atoms. OK, so to push this a little bit further, we can look at a condition where now we have 180 atoms. We no longer are going to enforce the condition that we perfectly rearrange them. So there's some chance that we have like a defect in our system. And then we can let the system go. So if we do that, we'll prepare this. Goes. Okay, get the point. And so we can compare statistics accrued on that system against a different situation where we try to controllably add distinguishability to the experiment. And so the idea here is that we can't really do calculations in this regime. We just want to figure out if there's some in situ way of simulating the physics of distinguishable particles where we're controllably adding that distinguishability. And so the idea is we can run experiments where we move where the atoms start, and we average over different experiments such that if you take into account all initial conditions, it's a full covering of the initial condition for the fully rearranged system. Does that make sense? So we move the atoms around, and we do it and the number of labels in this distinguishable situation is the number of times I have to move the atoms around in order to cover the whole lattice. So what we find is that as we add more and more labels, the Chechnovich criterion that we were using, this falls further and further down. This gray line here is where we can still calculate things. And furthermore, we can look at other ways of analyzing the data, like the distribution of outcomes for actually the survival. So this P here is the survival, the outcomes as a function of atom survival. If we just have the data in the experiment without adding these labels controllably, we see one distribution which moves further and further over as we add more and more labels to the experiment. OK, so that's the story that I wanted to tell you on this sort of bosonic atomic, or this atomic boson sampler. I just want to point out that there are a lot of different things that one can look at with this. So for instance, we could imagine other kinds of experiments looking at quantum optics with scalable Fock state inputs. Going back to things that I used to think about that I'm quite interested in, we could switch isotopes to an interacting isotope. This one was non-interacting, but we could switch to an interacting one. And there's a lot of interesting physics that we could look at, including looking at entanglement measures, which we can now measure more efficiently. It's very hard to measure entanglement in these systems because you need many, many, many runs of your experiment. So by making your experiment faster, you're able to do this more easily and more scalably. Finally, one interesting question at a sort of theoretical level is whether this could be used to improve the temperatures that one can access in fermionic systems. I think this is actually pretty not obvious, but also very interesting. OK. All right, so I have like 10 minutes left. Is that right? OK. All right. So let me pivot here. OK. So this part of the talk is really about qubits. Sort of like, what do we want in a qubit? All right, so what do we want in a two-level system or a qubit? So just to be clear, I'm talking about, a two-level system. And there are different sort of parameters of interest here. So there's the energy splitting of the qubit. In some situations, you care about that. There's the rate at which you can drive population from one state up to the other state and back down. So for instance, you do rotations on a Bloch sphere. So this tells you how quickly you can manipulate your qubit. There are also other considerations, like how stable is the energy of this splitting. So I'm showing you this like energy flopping up and down. There's also the possibility that your system's not closed. It might release a photon to the environment, projecting out your qubit. And both of these processes might take some coherent superposition that we care about with some phase phi and turn it into some mixed density matrix with some time scale tau, like coherence time associated with that process. So like the rate at which this pure quantum state turns into something that's actually mixed. And so typically when you're designing qubits, depending on what you're doing, these three things matter. They don't necessarily all matter, but each of them might matter. And so the last thing that you care about is having many identical qubits, which really sort of have all of these parameters in common. And so this part of the talk, which will be very short, is that alkaline earth atoms not only always come the same, and this underlies their use in optical atomic clocks as well, but they have some very, very special properties in the two-level systems that they host. So this is, again, the spectral structure of an alkaline earth atom. In the first part of the talk, I was really focusing on how we use this cooling and detection to sort of enable the physics that I was describing. But there are other things of interest. So for instance, there's this clock transition for which alkaline earth atoms are perhaps most famous. And there's also, in alkaline earth atoms, a nuclear spin, which importantly is in a j = 0 state. And I'll describe in a moment why that's important. And actually, there are different species of atoms, of alkaline earth atoms, each of which have different amounts of nuclear spin. But one that's particularly nice is ytterbium-171, which is a spin 1/2. So the nuclear spin is like this perfect qubit. It's a two-level system, and it's not only that, but it can be very well isolated. And there's also, you can think of the clock transition as its own qubit, except it exists on an optical transition. So the main difference between this guy and this guy is the fact that this one exists on a transition that's hundreds of terahertz, so that omega naught that I was describing, versus this guy here, the nuclear qubit, it can be anywhere from 10 to 100 or 1 to 100 kilohertz. Okay, so completely different energy scales. So one thing I'll add is that in addition to having these different qubits, it turns out that alkaline earth atoms have very nice properties for entangling the atoms using something known as Rydberg interactions. These are dipole-dipole interactions. When you excite an atom to some high-lying level, the electron clouds get very fluffy, and they're more likely to interact. And we use that for quantum information processing and entangling qubits. OK, so I'm going to focus on this part in the remainder of the talk, and I'm actually going to skip this part. And I think I have enough time, so that's good. OK, so nuclear qubit. I said it was inherently robust. What do I actually mean by that? So a problem that we run into is that we have an atom in our trap. This is a picture of our trap. And the atom might move around, or the trap energy might fluctuate because we're not controlling a laser power well enough. And often what happens is that the qubit energy, the splitting omega naught, that might fluctuate as a result of these fluctuations in the tweezer potential. So that means that you have some omega naught, which has some noise in it, delta omega. And so, for sort of like to have in your head, if I wanted a 1 second coherence time, I'd want this delta omega to be less than a hertz. Okay? And this is hard because this energy scale here might be a megahertz. So you really need to make sure that this qubit splitting is stable at a level of part in 10 to the 6 if you want to have this kind of quality. So for reference, in alkali atoms, so single electron atoms in their valence shell, the T2 star, which is the coherence time that people typically care about, is on the order of milliseconds. It's sort of a millisecond to tens of milliseconds. There's like one outlier experiment that does something very fancy, but usually this is where we're at. This is, depending on your audience, a provocative point, but it's true. The nuclear qubit, on the other hand, can be hosted in the singlet S0 state or that triple P0 excited state in the clock. And it has this important property, which is that this number here, if you're not in this world, is the J quantum number. And the reason in this situation here you have fluctuations in the qubit energy is because of something that we're doing to the electron. When I trap an atom, think about it semi-classically. I have some oscillating electric field. It's going to be talking to the electron. But if the nuclear spin is not coupled to the electron, then that doesn't matter. And the key point is that if J equals 0, then the hyperfine coupling, which hybridizes the nuclear spin I with the electron angular momentum J, if J equals 0, then this hyperfine coupling is 0, and therefore the nuclear qubit does not know about what you're doing to the electron. Okay? So these things go away. And as a result, these effects that I was just describing, those two go away. Okay? All right, so we can see this in Ytterbium-171. So this is recent data from the lab. This is a measurement of the T2 star coherence time. What that means is we do 2 pi over 2 pulses. We wait some time t, and we ask, is there a fringe? Okay? And we see out to about 4 seconds that we have the contrast of this Ramsey interference persist. And this can be true even in a 2.3 megahertz deep trap. Okay, so what that means is that this trap is super deep, but it's not even perturbing the qubit very much at all. And in fact, we don't think that this dephasing that we observe has anything to do with the trap potential. Furthermore, the T1 depolarization time, this is the amount of time it takes for the spins to mix, say for one to couple to the other one or the other one to couple this way due to, say, scattering from the trap. This can also be very, very long. And it's independent of trap depth. So what I'm showing you here is that as we change the trap depth, that's the green, the T1 time is unchanged. This would be unheard of in an alkali experiment. So I don't mean to be sort of like bashing alkali experiments. There are many wonderful alkali experiments, but I'm just trying to explain this story. But what we do find is that as you change the magnetic field, it improves the T1 time even more. And we think that's because of magnetic field noise in our lab. OK, so that tells you about the coherence properties of this qubit. But on top of that, we can also do operations on it. So here we're doing optical 2-photon Raman transitions for the experts, where we can do a rotation around the x-axis of the Bloch sphere or the z-axis of the Bloch sphere. And we see that these can persist for many oscillations. We can also do these oscillations these rotations very quickly. So the time scale here is microseconds. And importantly, we can do randomized benchmarking. This is a technique for in a sort of platform agnostic way, diagnosing how good your single qubit gates are. And what this plot is showing you is that we can do basically nearly 1,000 gates. I think this went out to 500 gates. Joanna can correct. 500 gates, OK. And the purity of the atom, of this qubit, only drops by about 20%. OK, so after 1,000 gates, the errors are compounding only at the level of about 20%. So we have good coherence time, and we can do two good operations on this qubit. The last thing that I want to point out is that a very important thing in this world of quantum computing is being able to do something known as mid-circuit measurement. Mid-circuit measurement is the idea that I have some set of qubits, and suppose I have just a handful over here that I want to measure without touching the rest. Okay, this can be, it sounds like it might be easy. So like in a superconducting qubit system, it actually is easy. But basically in atomic systems, it is not easy. And that's basically because when you shine a light and you want to detect the atom, that light can be, your qubits are very, very sensitive to that light. The reason mid-circuit measurement is important is for things like quantum error correction. I think people probably saw a lot of slides on this. Let me just very briefly say what I mean here. So this is a grid of qubits. There are black qubits and white qubits. Let's just focus on this circuit here. So this corresponds to one region of this so-called surface code here. And the idea is this black qubit, we call that an ancilla or a measure qubit. And in quantum error correction, and specifically for this surface code, what one does is you prepare this qubit in some state G, and then you do a 2-qubit gate between that qubit with the A qubit, and then the B qubit, and then the C qubit, and then the D qubit, OK? And then you measure, right? But you want to measure without projecting A, B, C, and D. You just want to measure that black qubit. Therefore, you need mid-circuit measurement. And you do this on all of these guys in parallel, because if I just do this on this guy, I can actually infer whether or not an error occurred on these qubits without projecting them out. So in other words, if I see one outcome on this black qubit, I know that everything is good. Whereas if I see another outcome, I might find that everything is bad. But by doing this on all of these qubits at the same time, not only can I know that an error occurred, but I can infer where that error occurred. Okay, that's the key point. And so all this relies on mid-circuit measurement. Our lab is very interested in doing this. This is actually how you would do it. I'm not going to go into detail on this point. I just want to show, I want to highlight that this is actually a collaboration with Andy, who I think is not here right now, but nevertheless, yes. OK. So how do we do this with Ytterbium-171? So we use this clock transition here, the one I was talking about earlier, where there's this excited state, triplet P0, and then there's this bright state that we can detect the atoms with by just driving a transition to that state, and then the atoms decay, and we collect those photons. And the idea is as follows. We want to be able to take population from here and put it up here so that atoms that are up here do not see this detection light. Okay? And to make that work, we really need to be able to do high fidelity rotations on this transition. We spent basically 5 months trying to do this, and we now are in a regime where we can have pulses on this transition with 10 to the minus 3 error. And we can use this to do mid-circuit measurement. And so the idea is as follows. So we have an array of qubits. Half of these qubits are our measure qubits, the ones that we want to measure first. The other half are our data qubits, the ones that we want to preserve and measure later just to make sure things are working. And so what we do is we have our qubit down here, and then we can drive a pi pulse. I'll call that operation S1. You'll see why in a second. I can shelve the qubit up here. And what I can do then is the following sequence. So I do a pi over 2 pulse on the qubit. One of the qubits I can shelve using what I just showed you, that S1. But the measure qubit, the one that I want to measure first, I can suppress that operation by shining a tweezer on just the measure qubits, which shifts this energy out, this transition energy out of resonance. So we're doing site-resolved shelving of the qubits. And so we see this when we measure the measure qubits because they don't get shelved. But then once we later bring the atom in the data qubit atoms back down, we can see that their coherence is pretty well preserved. And so this is a very nice way of doing parallel mid-circuit measurement with nuclear qubits. If you try to do this with other atoms, it can be very complicated. And it's very nice that we basically have these dual qubit degrees of freedom of the optical qubit and the nuclear qubit. OK. I'm going to end there. I'll just say that my group has also done a lot of work in optical atomic clocks, but I'm going to not talk about that. So let me end there and just get to the end of my talk. I can use this nice feature, right? Except I show you how badly I estimated the length of my talk. Okay, good. So let me just highlight the people involved here. For the clock work I didn't talk about, we've been collaborating with the Yi group here. The strontium team is mostly on the right. Will Eckner didn't make it on this hike, but he's floating over here. Aaron Young, Alec Tal, and Nelson Darkwa Apong. Alec, who should be over here on the ytterbium side, was involved in the ytterbium work, along with Aruku Sanu, Will McGrew, and Joanna Liss. Matteo is on the cryo team. I had a slide on it, but I wasn't able to show it because I ran out of time. And also Kei Zhao, who was involved in some other work. Go ahead. Thank you.
Great. So why don't we just take a few minutes for a couple of questions? Go ahead.
So for the mid-circuit measurement stuff, can you also do repreparation?
Yeah. Yes.
So, how?
Yeah.